In respiratory physiology, the respiratory gases are often quantified using partial pressures. We use partial pressures to talk about the amount of gas within a gas mix, but also to talk about the amount of gas that's dissolved into a liquid phase. First, the partial pressure of a gas within a gas mix. This is a straightforward application of the partial pressure. The partial pressure of a gas within a gas mix is the product of the percent composition of that particular gas within the mix and the total pressure of the gas mix. As an example, atmospheric air at sea level has a total barometric pressure of approximately 760 millimeters of mercury. Atmospheric air is comprised of a mix of gases, predominantly nitrogen and oxygen, but then other trace gases as well. Approximately 21% of atmospheric air is oxygen. This means that at sea level, and assuming that the air is dry, meaning not humidified, then the partial pressure of oxygen is approximately 160 millimeters of mercury. This is in contrast to a dissolved gas within a liquid phase. Different gases can have different solubilities based on their chemical structures and how they interact with the aqueous solution. So in respiratory physiology, when we talk about the partial pressure of a dissolved gas, what we're referring to is that there's a sufficient amount of this gas dissolved to produce an equilibrium where there's no net movement between the gas in the gas phase and the dissolved gas in the liquid phase. In order to understand why this is the case, you have to first consider how gas molecules move between a gas phase and a liquid phase across the liquid-gas interface. Now imagine a situation where you have a chamber half filled with liquid. We'll just make it water to keep it simple. And the upper half of the chamber is occupied by some gas of a given partial pressure. The gas molecules are zipping around the upper half of the chamber, making collisions against the wall of the chamber, and also making collisions against the air-water interface. When a gas molecule collides with the air-water interface, it can become trapped into the liquid and thereby become dissolved. The rate at which gas molecules move from the gas phase into the liquid phase is proportional to the number of gas molecules within the chamber. If the number of gas molecules in the chamber is low, meaning it has a low partial pressure, then the rate at which the molecules become trapped in the water is relatively low, that it has a low rate in, meaning a rate into the aqueous solution. In contrast, if the gas has a large number of gas molecules, therefore a very high partial pressure, then the number of collisions at the air-water interface will be elevated, producing a much larger rate in. So the rate at which gas molecules move from the gas phase to the liquid phase is proportional to the partial pressure of the gas. Just as the gas molecules can enter the liquid phase, they can also contact the air-water interface going the opposite direction, moving from the liquid phase back into the gas phase. When this occurs, they become liberated from the water molecules and rejoin the rest of the gas out in the gas phase. The rate at which the molecules move from liquid back to gas is a function of two parameters. First of all, it's based on the concentration of the gas molecules dissolved in the liquid. If there is a low concentration of gas molecules, this produces a low rate out. Conversely, if there's a very high concentration of these gas molecules dissolved in liquid, the probability that gas molecules will reach that air-water interface will be elevated, therefore there'll be a greater rate out. But the other parameter that determines the rate out is the solubility of the gas. The solubility basically describes the nature of the interaction between the structure of the gas molecules with the water molecules. Some gas molecules will develop relatively strong interactions with their neighboring water molecules and therefore will have a high solubility. You can think of them as being easily trapped or relatively sticky to the water molecules. Conversely, other gas molecules can have a relatively low solubility, meaning that they don't interact very strongly with the water molecules. You can think of them as being relatively hydrophobic. The amount of gas dissolved in the liquid phase is a product of partial pressure of the gas within the liquid phase and the solubility of that gas for the liquid. To illustrate this relationship, let's imagine that you're conducting an experiment. First of all, let's imagine that, again, you have this chamber halfway filled with liquid, and you fill the top chamber with some gas. Let's say that this is a gas with relatively high water solubility. And let's also say that the partial pressure of this gas within the gas phase is 100 millimeters of mercury. Now, at the instant that you start this experiment, let's assume that there's no gas dissolved in the liquid. So you put the gas in the chamber, you seal it up, and you watch what happens. At the start of the experiment, the gas molecules colliding around in the upper half of the chamber make contact with the air-water interface and become trapped in the liquid. Again, this occurs at a specific rate based on the partial pressure of our gas, 100 millimeters of mercury. This is our rate in. At the outset of our experiment, the rate out is 0 because we assume that there are no dissolved gases in the liquid. But as the gases become dissolved in the liquid, the concentration of the dissolved gases begins to increase within the liquid phase. As the gases begin to accumulate in the liquid phase, this produces a small rate out. If we assume the concentration in the liquid phase to be relatively low, then we could expect the rate in to exceed the rate out. Therefore, we still have net movement of gases into the liquid phase. This causes a further increase in the concentration of the dissolved gases in the liquid phase, further increasing the rate out, and eventually we'll reach a condition where the concentration of dissolved gases in the liquid is high enough to produce a rate out that is equal and opposite to the rate in. When this occurs, there is now no net movement of gases between the gas phase and the liquid phase. And under these conditions, we say that the partial pressure of the dissolved gas in the liquid phase is equal to the partial pressure of the gas in the gas phase. In this case, that would be 100 millimeters of mercury. Now let's compare that to a situation where we repeat this experiment, but we do this with a lower solubility gas. So this is a gas with low solubility for water. So as soon as we start this experiment with a low solubility gas, we observe what we saw before. That is, rate in far exceeds the rate out. Therefore, we have net movement of the gas molecules into the liquid phase. But note, because this gas has low solubility, it tends to move from the liquid phase back to the gas phase much more readily than the high solubility gas. And in fact, because it moves so readily, it'll reach an equilibrium between the rate in and the rate out at a much lower concentration of dissolved gas within the liquid phase. Even though the concentration of the dissolved gas within the liquid phase for this low solubility gas is much less than the dissolved concentration of the high solubility gas, nevertheless, we would say that the partial pressure of the dissolved gas in the liquid phase is 100 millimeters of mercury. So there you have it. We have two gases. One has a low solubility, the other a high solubility. But if the movement of each gas is in equilibrium between the gas phase and the liquid phase, and we assume that the partial pressure of the gas in the gas phase is the same for both the high solubility and low solubility gases, then that means that the partial pressure of the dissolved gas in the liquid phase is also the same, even though the dissolved concentrations are different. So in respiratory physiology, this scenario mimics the behavior of oxygen and carbon dioxide. Oxygen has relatively low solubility in water, whereas carbon dioxide is highly soluble in water. Carbon dioxide is approximately 20 times more soluble in water than oxygen is. Because oxygen has relatively low solubility in water, our blood requires specializations to transport oxygen, namely hemoglobin, to increase the oxygen carrying capacity of our blood. So why do we talk about these gases in terms of their partial pressures, even though it makes it difficult to make direct comparisons between gases that have different solubilities? Partial pressures are useful because they allow us to determine the direction and magnitudes of partial pressure gradients, which will determine the direction of gas diffusion between the pulmonary blood and the alveolar spaces in our lungs.